Okay, so we have an honor to start this session with the talk by Dr. Filimonova, and the title is the X-ray absorption spectroscopy on PGE minerals. Thank you. The floor is yours.
Yeah, my name is Olga Filimonova. I usually don't have a too loud voice, so if I'm not loud enough, please raise your hand, okay, so I can see. Okay, thank you. Today, thank you for this opportunity to present this talk. And today I'm going to show some results. Some results on characterization of platinum group elements in different minerals performed by X-ray absorption spectroscopy. Then we talk about XMaS method, it's abbreviation for X-ray absorption spectroscopy. We usually talk about synchrotrons. I work at the European Synchrotron at Grenoble in France at the British beamline. What makes ESRF special, that now after upgrade in 2020, it's called extremely brilliant source. That's because it has extremely high flux in the nutshell. And but it was not always the same. That if we look at the history, starting from the beginning of 20th century, then X-ray were described and discovered and described. That, for example, the characteristic X-ray already was discovered in the very, very beginning of 20th century. But unfortunately for XIS, the energies of the X-ray tubes, which were used, for example, for XRD analysis, were not enough. The flux was not enough. So XIS method was awaiting for the invention of the synchrotrons. And first synchrotrons usually looked like toys for us now. Now they are much bigger. And it took another more than 30 years to scientific society to build their first synchrotrons, which will be working in the user mode like we know them now, which is the 80s, for example, the Daresbury one in the UK, which I'm sure everybody heard about. What makes XIS method special, that it's an element-specific method. It's sensitive to oxidation state and local atomic environment. And due to the, yes, it's a local method, but at the same time, it's the strong point of this method is that we can characterize the very wide range of materials, including the powders, crystal materials, and even amorphous and disordered materials, including liquids, for example. And of course, as any method, the best way of using it is together with the other ones. It's not solving problems by itself. It's unable to solve problems by itself. Before discussing a little bit the challenges and their advantages of the method, I would just like briefly remind you, I'm sure most of you know how XIS spectrum looks like. Just a reminder that it's nominally divided into two parts. One is called near edge structure, and this part is near the absorption edge. Then we use kind of slangish words, but these are in fact terms which are used in the papers, which are edge jump. This is the absorption edge, and first intense peak we call white line. That's basically almost all the terms you can find. And XANES is extremely informative part of their spectrum. It can, through comparison with the standards, we can get information on the local atomic symmetry. For example, we can discriminate between octahedral and tetrahedral state. But the coolest thing that we can also discriminate between different geometries, even if the coordination number is the same. For example, we can distinguish between tetrahedral and square planar symmetry. Then in case if we have their similar polyhedra, surrounding the absorbing atom, but the sort of the atom is different. We also can discriminate between those states. Here is example for platinum. And of course, we can define the formal oxidation state, which might be different from the real one, but from the idea that our bonding is purely ionic, we can define the formal oxidation state. Yeah, and also we can apply different ab initio methods like the MES and FEF and simulate this spectra, having the XYZ coordinates, and compare them to the experimental ones, also, which also sometimes is helpful, can be helpful in interpreting the experimental results. Yeah, if we continue recording, we will record the extended fine structure. This region of XMaS spectrum tells us everything about neighbors, about interatomic distances, coordination numbers, and types of the neighboring atoms. Just very briefly, that if we recorded the full XMaS, we can extract exact function, and performing Fourier transform, we will be able to see the local atomic environment of the absorbing atom, which is normally will be in the 0. And then here x-axis would be corresponding to the interatomic distance between the absorbing atom and the coordination shells, where every contribution would be their coordination shell. First one, second, and so on. So here it's 6 sulfur atoms, it's PTS2. Yeah, and now I just want to emphasize some challenges and maybe advantages of the method, which might be useful for everybody. And I nominally divided this, let's say, experiment into 3 phases. Like, then we're looking at the composition of the sample, then we're acquiring the data, and then we're processing the data. Although it's not a cooking recipe, there are books, monographies written about every single part of this little scheme. So yeah, don't get this as a final plan. So the big challenge of the XIS is that unfortunately it's an average temperature. If you record the spectrum, and if you have a few phases, you will get the average temperature on hospital, which will be 36.6. Everybody will be absolutely healthy. So here is absolutely the same. So in case of the powders, you understand that you can analyze by XRD, for example, analysis preliminary, right? And to find the admixture, which you will have to discriminate in the end from your spectrum of interest. The best way not to have it at all, but we're not living in the ideal world. If we're working with the polished sections, we have to be extremely careful with the size of the beam. Because, for example, this pyrite, if it contains, for example, micro-inclusions of gold, and if we choose unwisely their spot, it will be very hard, if not impossible, to discriminate between gold in pyrite and gold in this slate. But as often happens in life, that what is the curse, is a bless of the method. And here is an example. This is a palladium-bearing pentlandite. It's extremely enriched in palladium, while the pyrrhotite, coinciding with it, almost empty from the chemical point of view. It's almost empty in palladium, even if it's a few hundred ppm. So if you want to record the spectrum of XIS in this crystal, if we are touching the pyrrhotite matrix, it doesn't matter. It almost doesn't exist for us. But if we are doing it other way around, you have to be extremely careful, because one little crystal of pentlandite in this spectrum, and we won't be able to discriminate. Well, we will be able, but it will be much harder. Yeah, so indirectly we can use it also for discrimination of the phases if we know, if we have some clue about end members also of the kind of end members of our mixture. The other, I would say, important step on the preparation of the sample is the surface that in case of if you're recording the spectrum in the with the polished section, is ideally it should have their good surface, but I think in geological community is not a problem. Is that there are more sensitive methods which are more sensitive to the inhomogeneous, let's say, surface. So I think for geologists it's not too much of the question. Yeah, and again, this is division on is nominal on the sample composition and data acquisition because of course they are interconnected. So the next, let's say, group of problems may come from the concentration rate. So the concentrations can be too low. For example, in the case of the low concentration, we can hit the detection limit of the beamline, which is in the most of the beamline would be hundreds of ppm, maybe hundreds of ppm, and it may be specific dedicated beamlines for very nice compounds which don't give high background. It can be even ppb level, but yeah, this should be always negotiated before the experiment. So if we hit the detection limit, we won't be able to see anything. And even if we are not hitting detection limit, we might have some matrix effect. So here, this is the XRF spectrum, and you see that it's a silver in galena. This is the silver. This is our element of interest, and it's buried under the background, both because the matrix is very heavy because it's lead in galena, and because because the concentration of silver in this particular sample is extremely low. The next group of problems might come from the fact that the concentration is too high, unfortunately. In some cases, ideally we want to record all the photons on our detector if we are working with the fluorescence detection mode. Sometimes our material can absorb this signal by itself, so we will lose part of the signal, which is very unfortunate. And we might sometimes also the problem interconnected with a high concentration is the oversaturation of the detector. But again, I think this in geological community also known because it's a microprobe dead time definition. So it's exactly the same problem. The next challenging thing is their resolution. I would roughly divide it into spatial and spectral. The spatial one, in terms of the spatial one, most common beamlines will be working with a beam size of the 50 to 500, maybe 300 microns. However, with their using, for example, KB mirrors, we can go to much smaller, to use much smaller beam, or using the unfocused beam, we can use even a centimeter size beam. So in this, I find this is amazing example from Lera Brovchenko paper, and you can see here that they used quite submicron size beam, and for a reason, because this is a palladium-bearing pentlandite, and around there are platinum group minerals. So if they would choose a big size of the beam, they would have a contamination of the signal, and it will be very hard to analyze it in the to process the data. Yeah, and for spectral resolution, depending on the mode, people might understand differently this term, because then we are recording XIS. We need first to set the region of interest around the emission lines. So we see here this XRF spectrum, and this is the channel. These are the channels of the detector. So and here is calibration curve. So depending on the calibration curve we choose, so for example 10, 20, 40 eV, of course channel will contain different amount of energy in eV. So we'll have different resolution spectra. And the other spectral resolution is concerning their directly XIS. Here we can usually we choose one of the modes. It's a total fluorescence yield mode, or high energy resolution fluorescence detection mode. The first one showed in black, and the third showed in red. And you can see that, of course, the compounds, the compound is the same here, it's both PTS, but in the HERV mode, we see the peaks are much more enhanced, which is much easier to analyze in the end. And unfortunately, platinum group elements have a very close, not only close chemical or physical properties, but also in terms of spectroscopy, they are also twin brothers. So this is only the example of osmium and iridium, but it is a problem which we encounter with all platinum group elements. Their emission lines are quite close, and the absorption edges as well. Where it can lead us? Well, here is an example. This is a sample containing both osmium and iridium, and we chose the region of interest here. And instead of having nice long XAS spectrum with a full EXAFS, we are getting the edge of iridium, unfortunately. So we are cutting part of the osmium signal. It's possible to overcome this problem theoretically or experimentally, but with the platinum group elements, it's always the thing to be concerned about. Yeah, and the last thing, I won't stop at this at all, it's time and access. So in the most of the cases, if we measure something with the XAS experiment, by XAS, we usually try to measure something in advance for the next experiment, because it's much easier to justify for the committee that your project is valuable if you already have at least one spectrum, even if it's a very noisy one. Yeah, and on the step of data processing, I would emphasize with like two maybe things which, in my opinion, might be important. So it might be very beneficial to know some coding language. It doesn't matter at which level, just the general understanding of the coding would be very beneficial. And unfortunately, like for example, then we are analyzing the LICE-PMS data. In principle, we can do it with Excel, right? So almost with hands. Here, there is the use of specific programs is almost obligatory. So these are one of the common ones. There are much more. Yeah, and now we can look at the examples. The first example, I work mostly with the platinum group elements in sulphides, but here I will give also one example on oxide. If we are not talking about minerals or platinum group elements by themselves, we're talking about admixtures in other minerals. So in the most of the deposit, there would be micro-inclusions of the minerals by themselves or intermetallic compounds, or so-called invisible or refractory form, which can be isomorphic solid solution or some kind of nano-sized clusters or inclusions. And the first example I want to show you is a state of palladium in pyrite. So we notice that the concentration of palladium in pyrite is increasing with the temperature through the rough assessment of the natural data and synthetic data. And we suspected that it might be the solubility, but in order to prove it, we need to prove or disprove that it's a solid solution. Because if it's inclusions, we cannot build any kind of thermodynamic model at all. So we synthesized the palladium-bearing pyrites. They contained very high concentrations of palladium, up to 2%, and the distribution was quite homogeneous. Then we performed XAS experiment. These are some standards containing palladium and our samples, which are almost identical. Look almost identical, and plotted the formal oxidation state as a function of edge jump of the sample standard minus metallic palladium. So comparison with the standards for this calibration curve shows that the formal oxidation state of palladium and pyrite is close to +2, which is quite logical because the iron formal oxidation state in pyrite is close to +2. Yep. Then we analyzed the local atomic environment of palladium and pyrite, and this is the fitting curve is shown with a red line. And what we see here, that palladium was surrounded by 6 sulfur atoms at this distance, and comparing to the theoretical value in the pure pyrite, the distance increased. However, in the rest of the coordination shells, the distances were close to the pure pyrite. So it's not a distortion, it's a expansion was disappeared already in the second coordination shell. So here we've shown that palladium forms a solid solution, and the kind of amazing thing here, but for me, pyrite is not that amazing, maybe for everybody, that we studied before the platinum, the same work, but the platinum, the state of platinum and pyrite, and what we noticed that there is a dependence of between the covalent radii of the atom and interatomic distance of metal sulfur for iron, platinum, palladium. Iron is a major component. Then we try to make an assessment of the solubility of palladium, and it depends on the temperature and obviously on sulfur fugacity, because we're working with the sulfur system, sulfur saturated system. So they calculated, this is maybe the major in the nature equilibrium is the pyrrhotite equilibrium, and the concentrations are varying quite a lot. So from ppb to a few hundreds ppm level. However, in the nature, I didn't emphasize on this, but on this first graph, then I showed the natural samples, the maximum solubility is a few hundred ppm, and these are like a few findings. So, and in our samples, we found up to 28%. So why? Well, in order to answer these questions, we plotted our data at the classical Toulmin-Barton diagram from the 60s. Our data is the solubility rate of palladium in pyrite. And we also plotted their kind of nominal main field of ore formation. And as you can see here, just in the most of the deposits on Earth, the sulfur fugacity won't be enough to produce the few weight, the palladium-bearing pyrite, which would contain a few weight %, because it's here. So in the most of the cases, we're getting the ppm level, maybe a few hundred ppm, like we see in nature. So in the nutshell, that this paper is already published, and the concentration of pyrite, of palladium and pyrite was quite high, a few weight %. We proved that it's a solid solution. The big palladium atom, of course, expand the first coordination shell, and the expansion is proportional to the difference between the values of the covalent radii. And we performed also the assessment of the palladium solubility in the pure pyrite. The next example is this is iridium L3H, experiment at iridium L3H. This sample was collected by Anton Kutyrev. So this is a native platinum, which contains micro-inclusions of something which Anton Kutyrev wanted to check what it could be. Let's say, they measured their composition by microprobe. However, their composition was quite variable. So they wanted to be sure if they have the iridium oxide, which nobody found before in nature, or not. So in order to do it, we used the XMaS method. So for starters, we performed the XRF mapping to find our sample at iridium L3H. This is the iridium L alpha, and this is the map on iridium L alpha. And you can see that we chose here 2 spots. Well, we chose 2 more, but these are the most end member-ish like. So this is with the minimum concentration of iridium, and this is with the maximum, and this is the place where those crystals are located, microcrystals are located. So we recorded XMaS spectrum in these 2 spots. This is XMaS, but we recorded as long as we could the XMaS full ones. Then we performed the FDMS simulations, and here are 2 of them. It's iridium in platinum and iridium in iridium oxide. And compared through comparison of with their standards, we realized that according to their XANES analysis, in this region, so in the most of the grain, we have iridium in the platinum matrix. So it's in kind of intermetallic compound. But in this spot, we have up to 25% of iridium and iridium oxide. Why 25? Well, because our beam is about 40, 60 microns here. And you could see that the inclusions were quite small. So we were covering the matrix around the inclusions. Yeah, and in general, for this system, what we found out, let's sum up. We also performed the exact spectra fitting, but I'm not showing it because it's quite repetitive. It will be quite repetitive, so I will be showing only the results. So iridium mostly enriches their native platinum, and the distance, this distance is extremely close, the iridium platinum to platinum in the metallic, in the pure platinum phase. So as expected, I would say. But also we detected by XANES and by exhaust analysis, we detected the contribution of iridium oxide with a typical interatomic distance of iridium oxide. Usually then we use both XANES and exhaust. It's almost 100% success. So we are sure in this. And interpretation is not finished yet because paper is in preparation. So apparently it was extremely, it was formed in extremely high oxidation conditions, but probably they were the local state. Yeah, the interesting part about this experiment, just in a few words, that setting of the beamline usually takes about 8 hours. And this experiment, since you see it's not the most hard experiment in the world, it took less than 24 hours. So it's very fast. Now we have the fast scanning mode at our beamline at PM28, and it will take around 6 hours. So I would say it's quite fast. Yep. And the last system, it's also in collaboration with Anton Kutyrev. So he's a source of the very interesting spectroscopically minerals. So he found the osmium-bearing pentlandite, and his question was, in which state do you think this osmium would incorporate into pentlandite? Because preliminary, he recorded some less PMS analysis, and you can see that osmium signal osmium is homogeneously distributed. If you look at the osmium and major components, iron and nickel of pentlandite. So, and the concentration is about 500 ppm. So it's a classical good example, easy example, let's say, to study by XANES. The pentlandite structure contains 36 cationic positions. 32 of them are tetrahedral and 4 of them are octahedral. So our preliminary hypothesis could be that osmium incorporates into some kind of micro-inclusions of the osmium-bearing mineral, or it could be solid solution in the tetrahedral or octahedral positions. So just since it's a pentlandite and it contains, it's not non-stoichiometric, it's stoichiometric, but iron and the amount of iron and nickel can vary. So there are plenty of works devoted to the distribution of iron and nickel between the positions, tetrahedral and octahedral. But in my opinion, maybe somebody would correct me. Most of the papers would state that they are nearly randomly distributed. So we didn't even try to distinguish between iron and nickel. And also, it's almost impossible by XAS because they have extremely close molar weights. Yeah, and there are not that many papers on how platinum group elements incorporate in the structure. But here, just on the slide, I put two things which I would say could give us a hint that the position could be octahedral where osmium incorporates. So the octahedral positions are more like flexible in terms of moving on the cations. And also the Makovsky and Karol-Müller noticed that they didn't notice, they proved that almost all palladium that they managed to put into pentlandite, to dissolve in the pentlandite, was in the octahedral sites. So in order to prove or disprove these statements, we deformed XAS again, and these are reference materials and the spectrum of osmium and pentlandite. Unfortunately, they are. I know that in this picture they look quite similar, but it's not quite like this. So if we look at the enlarged portion of this region, we see the differences. So our osmium and pentlandite is very different from osmium-2. And also we compared it to a few kind of standards, which is not quite standard, it's also sample, but we suspected that this Nazi platinum was enriched with the osmium S2 inclusion, and that appeared to be true. But now we can compare the osmium S2 recorded in our experiment, not from the literature like this one. So yeah, and what this comparison in the sum shows that overall shape of all the spectra shows that osmium is not metallic. Osmium and pentlandite has a different state from osmium in osmium S2. So we are certainly sure it's not a sulphide of osmium presented in pentlandite. Yeah, and the rest it's quite obvious because we saw the micro-inclusions before, so it's sulphide. We roughly estimated the formal oxidation state, the same principle as I showed before with the palladium. We collected data reference materials available in literature and estimated our standards, osmium chlorine free and osmium in inclusions of osmium S2. Their oxidation states were slightly bigger than they're supposed to be, because it should be +3 and this should be +4 from the formal oxidation point of view. And osmium and pentlandite was this strange number close to +5, but there is no osmium +5 in nature. So, and also these calibration curves certainly gives us slightly larger numbers than they should be. So we suppose that the state is close to +4 in all the natural samples in the green and red. Yeah, and the last slide on this system that about their local atomic environment. We already know that osmium in one of the samples, osmium was in the osmium sulphide inclusions, but we wanted to see, we clearly can see it from the very short exhaust signal. So what we found out that in these samples, osmium was surrounded by 6 sulfur atoms at the distance, which is extremely close to the distance in the pure osmium sulphide. So it's 100% osmium sulphide in these inclusions. And also we proved that, unfortunately here we are working with extremely short XAS spectrum, that even in this case, we can see clearly all their information, all the information. And osmium and pentlandite, even though we suspected the octahedral state, it's certainly not the octahedral state. We tried all the hypotheses I showed you at the first slide, and they didn't work apart from one, and it's a tetrahedral position. So osmium incorporation of osmium and pentlandite requires this. Well, sorry. That osmium and pentlandite is surrounded by sulfur and iron in the first, second coordination shells, and the interatomic distances are quite close to the pure ones in pentlandite, since their osmium radius is not that different from the iron and nickel. Yeah, and here we've shown that osmium incorporates in the solid solution in tetrahedral state and up to 500 ppm in this sample from Galminan ultramafic complex. Yeah, and to sum up, I want to thank you for listening. I know it's already 4th day of conference. It's getting harder every day. And I work at the XMaS beamline. It's a British beamline at ESRF. So I encourage you to submit to our beamline your proposals, or to submit to any other beamlines of the ESRF. And what makes XMaS special, I would say that it's very easy to remember, this short name, that we are working up to very high, in a very high energy range. Not every spectroscopic beamline would work. in this range. And the deadline is the 10th of September, in case you are interested. If you want to ask some questions, I will be very happy to answer, or you can reach me afterwards. Thank you.
Well, thank you for very interesting presentation. So is there any questions from audience? Or online? Do we have online questions? Yeah, so I was thinking, so I'm pretty interested in gold in pyrite and arsenopyrite. So how much the arsenic messes or makes it difficult for determining whether we have a gold as a metallic and as a solid solution?
I don't remember if yeah. So unfortunately, if you look at the gold and arsenic, they have these are the edges. No, I don't have emission line, but their emission lines are also almost overlapping. So, but there are ways to overcome it. For example, the use of the XMaS of let's say approach, where you're using the crystals to cut out the specific energy, where you can use, and we already been performing with my former group, we've been performing experiments on the determination of the state of gold and arsenic in pyrite using this method. So, but we are not the only ones who were doing this. So within a few years, I think 5 years, there are at least 4 papers using the same approach. So it is possible, but it's not straightforward, but it's possible.
Thank you. So any more questions?
Thank you, Olga, for your nice talk. I have a question related to the iron oxide. So I've seen that. I wonder if you carried out something like EBSD analysis of the oxide, or just say that your technique says the results you have seen.
No, I think there is a Raman, as we discussed yesterday.
I see. Okay, so just to understand, and I think the problem, especially when you give the percentages or the possibility to divide the iridium in the 2 phases, is related to another possible artifact you can have about the depth of interactions of your technique. So you say 10 microns, right, of the size of the crystals. But what about the depth of interactions of
these energies, it will be maybe even 30 microns.
Yes, so yeah. You are thinking that your phase is homogeneous down to that point.
Well, I'm not, I was not aiming for not touching the matrix, because it's impossible with a 60 micron beam. It's impossible not to touch this, the matrix around these microcrystals. So it's if it's the question, I'm not sure.
Yeah, as I'm only thinking about how to distinguish about the 2 phases.
Yes.
So I to hypothesize that the reconstruction of the volume of the samples you see in the polycid surface.
No, here it's well, using tomography maybe, but here no. You can possibly cut out the piece and by film, for example, and then measure it, but it's not that straightforward. So.
Okay, thank you.